Okie dokie. So we march on into Venema's section 3.4. We are still looking at neutral geometry. Neutral geometry is geometry that does not give a rip about the Euclidean parallel postulate or any other parallel postulate for that matter. And in this lesson, we concern ourselves with angle measures. And angle measures are made astonishingly easy to deal with just by having them be real numbers, because we get all of the properties of the reals, all of the algebra that goes with the reals. And so angle measure does for angles what distances did for segments in a previous lesson. This brings us to fifth axiom, the fifth of the 6 axioms that we will look at, and the last one that we bring up in chapter 3. Axiom 5 goes like this. It's called the Protractor Postulate for what I hope will be obvious reasons when we get there. For every angle, BAC, there is a real number, mu of angle BAC, called the measure of angle BAC, such that the following conditions are satisfied. And there are 4. First, the measure of angle BAC has to be between 0 and 180, those are in degrees, for every angle BAC. The angle could be 0, but cannot be 180, and that's an important thing to note. Venema is not going to allow us to consider straight angles. Straight angles do not exist. 2, the measure of angle BAC is 0 if and only if the ray AB is equal to the ray AC. And you should pause for a moment as to how that backs up our intuition. Okay, that's a good pause. Third, for each real number R, 0 less than R less than 180, and for each half plane H bounded by AB, ray AB, there exists a unique ray AE such that E is in the half plane and the measure of angle BAE is R. This is the part that really is the protractor postulate. So if I have a ray AB, and I choose some number, maybe R is 10. One moment, please. Sorry, needed to sneeze. Anyway, there exists a unique ray AE on this side and also on this side, such that that's a 10-degree angle, that's a 10-degree angle. For each half plane, there's a 10-degree angle. And no matter what number R you pick, you can generate that angle. This is important because it drives home the one-to-one correspondence idea. You've got one-to-one correspondence. For every real number R, there is a ray. And we should talk about the fact that the ray is unique, but clearly the point E is not. I mean, E could have been this point, it could have been this point, it could have been this point, and you have had enough of me talking about that. Right. Anyway, that's all we need to say about that. That's really the protractor postulate part of it. No matter what number I pick, if I want a 62-degree angle, I can get it on either side of ray AB. Okay, and then 4, if ray AD is between ray AB and ray AC, then the measure of angle BAD plus the measure of angle DAC is the measure of angle BAC, and you should pause to draw rays AB and AC, and then to have a ray AD in between them, and make sure that this is a statement of what you believe to be an intuitive notion. I'll give you a moment to do that. You should probably draw. You should also think about how this axiom in all of its parts holds up to your scrutiny of geometry thus far? Does this match up with what you think of when you think of angles and making angles and measuring angles? Does this hold up? I hope so. You should also think about a couple of other notions. You should think about, what it means to have a right angle, what it means to have an acute angle, and what it means to have an obtuse angle. And yes, we're going to go with the basic definitions that you may remember from high school. Can we generate right angles? Can we make sure that there is a 90-degree angle that matches up with any ray we choose? Gosh, I hope so. And then acute angles, where will they fall? And then obtuse angles, where will they fall? So all of the terms that should be familiar to us from all of the geometry we've ever studied should be familiar to us in this geometry, because this is a superset of everything we've ever done. Okay? Okay. We are on our way to betweenness, and since we are on our way to betweenness, instead of presenting one giant proof, we present two smaller proofs, one of which is necessary for the other. And when we do a small proof on our way to a big proof, we call that a lemma, and so this is a lemma that Venema brings to us. If A, B, C, and D are four distinct points, and if C and D are on the same side of line AB, and if D is not on ray AC, then C is in the interior of angle BAD, or D is in the interior of angle BAC. We should pause for a picture. We've got A, B, C, and D. Oh, I should have here. Let's draw that. And then pausing long enough over here, let's draw that. And let's make sure that these, that's what I wanted. Okay, I'm a good teacher. You don't really have to meet in that, but okay, good. So in this case, we've got line AB. Oh, is that terrible? That is terrible. I'm using a pen and I missed that. That's line AB. We have D not on ray AC. We've got four distinct points. We've got C and D on the same side of line AB. So either C is in the interior of angle BAD, or D is in the interior of angle BAC. And clearly it's true if you draw the picture like this. This is C. Clearly it's true if you draw the picture like this. Clearly it is also true if you draw the picture like this. It is also true. So the question is, how do we prove such a thing? How do we prove such a thing? And the key to this proof, as you will all remember from Math 239, is in the word or. When we see a proof where we have to prove that one thing is true or another thing is true, the way we traditionally do that is we say, let this one not happen and show that this one must happen. We assume that the one of them cannot happen and prove that the other one must happen. We could go the other way. We could assume that D is not in the interior of BAC and then show that C must be in the interior of BAD, but it suffices to say, let's have C not be in the interior of BAD, and let's show that D must be in the interior of BAC. Okay, so that's the gist. So we're going to assume C is not in the interior of BAD. So C is not in here. Since C is not in there, then C and B are on opposite sides of ray AD. They are on opposite sides of ray AD. That only makes sense. And since they are on opposite sides, when I draw a line segment from C to B, guess what that line segment has to do? That's right, that line segment has to hit ray AD at some special place. Call it chicken nugget. We will call it chicken nugget. That is the special place where the segment CB hits ray AD. So, in particular, C and chicken nugget lie on the same side of line AB. So, if C and chicken nugget lie on the same side of AB, A is not between chicken nugget and D. And so the ray from A through chicken nugget is the same as the ray from A through D. That's the same ray. This red ray has to be the same as the blue ray AD. Oh, blue ray, nice. I don't have one of those. And so therefore, D has to be in the interior of angle BAC by construction. Okay? That's a lemma. We are going to need it. Very well. We're going to need it because of this. If A, B, C, and D are four distinct points such that C and D are on the same side of AB, then the measure of angle BAD is less than the measure of angle BAC if and only if ray AD is between ray AB and ray AC. So, picture time. You've got A, B, C, and D. You've got line AB. C and D are on the same side of line AB. Then the only way for this angle measure to be less than angle BAC is if ray AD lies between ray AB and ray AC. This is intuitive, but it's not intuitive enough to make an axiom. We can actually prove this based on our previous work. A little bit of Math 239 introduction to proof for you. If and only if. If and only if means we have to assume the one and prove the other, and then assume the other and prove the one. I'm going to go this way first. I'm going to assume that ray AD is between AB and BC, and then I'm going to show that angle BAD has to be less in measure than angle BAC. That's the plan. So, here's the way we do that. Let's assume that ray AD is in between AB and AC. Well, what does that mean? That means that the measure of angle BAD plus the measure of angle CAD is equal to the measure of angle BAC. That comes down to that stuff we talked about with betweenness. So if AD is between AB and AC, then I add up the two smaller angle measures, I get the big angle measure. But we know, what do we know about this angle? We know that this angle has to be positive. And if that angle has to be positive, then by definition, and a little bit of algebra really, angle BAD has to be less than angle BAC, because we have angle BAD plus some positive number is the measure of angle BAC. This almost makes sense. To go the other way, that's trickier. That's a trickier thing. So instead of assuming that one angle measure is less than another, we're actually going to work this through by contrapositive. we're going to go with the contrapositive. We're going to assume that AD is not between AB and AC. We're going to assume that AD is not between AD and AC. So if AD is not between AB and AC, there are two options. One is that AD is this purple ray, and the other is to assume that AD is that purple ray. If D is on AC, if you get the first case, then clearly, so if D is on AC, then the measure of angle BAD is equal to the measure of angle BAC, and that's what we want. Because in a proof by contrapositive, we try to prove the opposite of the thing we want. And the opposite of less than is greater than or equal to. Well, if D is not on AC, if it's the second case, then C is in the interior of angle BAD. And that happens by the lemma. The lemma that we had on the previous page, and you can go back and look at it. The lemma says either one is in the interior of the other, or the other is in the interior of the one. And so in this case, C would be in the interior of BAD. And if C is in the interior of BAD, then that necessitates that angle BAD has to be bigger than angle BAC by the first part. I mean, that's just what we did up top. And since we've got it going the one way and we've got it going the other, we have betweenness in terms of angle measures, which is great, because if you can get betweenness in terms of angle measures, you can get all sorts of fun results. Okay, so that's all I want to say about 3.4. Those are the things that you need to know in 3.4. I hope that they are helpful to you, and we'll do 3.5 coming up quick.